the last video, you learned a little bit about thermochemistry and the equation Q equals Cm delta T. In this video, I want to show you how data is collected in a calorimeter for a thermochemistry experiment. So what is calorimetry? Well, it's measuring the heat flow in or out of a system. Remember that the system is the part of the universe that you are studying the heat content of. Usually it's your reaction. Now, heat can be released, like an exothermic reaction, or it can be absorbed, like an endothermic reaction, during these different chemical reactions. And we monitor that with a change in temperature. So you have to have a closed system for this to occur. The system we use, the container, is called a calorimeter. It's a closed system under constant pressure because we do put a lid on top of it, and it's a metal chamber usually, so it maintains its volume. So any heat that is released or absorbed is only from the contents of the calorimeter. Now here's a picture of a calorimeter. It's called a bomb calorimeter. And the way that it works is you see the metal container there. There is a thermometer that's in some water with a stir, so you maintain good heat movement in the water. A sample of the reaction is put inside a small cup in a smaller container inside the bomb calorimeter. The oxygen that's in that cup is then ignited through some wires, and as the reaction happens, in this case the sample would burn, the heat that's released from the reaction would warm up the water, and you would measure the change in temperature with the thermometer. Now here's a video clip of an actual bomb calorimeter that I made while I did some research one summer in a lab. So what you're going to see now is an actual calorimeter. We don't have one in our lab, but this was something at a university lab. Take a look. This is a bomb calorimeter. This is the actual piece of equipment that researchers use to calculate the energy content of either biodiesel or maybe even the potato chips that you had for lunch today. When they calculate the amount of energy, they're going to calculate it in heat units, which would either be joules or calories. I want you to look inside the bomb calorimeter. Inside here, you can see that there's a silver bucket. Water goes all in here. And this is actually the bomb. It's a smaller silver cylinder. What you do is put your fuel sample in there. Then, these two electrodes are connected to the bomb. These provide the spark that will ignite your sample. When your sample burns or combusts, that gives off energy. So how is the energy collected, or how does a scientist figure out how much energy is being given off? Well, it's a closed system. There's a lid here that goes on top of this calorimeter. And what's in here in the lid is a stirrer. The stirrer is going to stir the water that's in this big pool here, so that the heat given off from the sample is going to warm the water in a uniform way. This is the temperature probe. This goes down in the water also and measures the change in temperature, because as the sample is burned, it'll give off heat and the temperature of the water will increase. So the lid goes on, the sample is prepared. The last thing that you need to make a combustion reaction happen is oxygen. And at some point during the process, some oxygen is added by a tank that's connected to the calorimeter here. So we are going to burn a sample of the biodiesel that you've prepared and get some feedback on the energy content of it. You'll be able to use this to compare it to petroleum-based fuels like octane. Now that you know how the calorimeter works, I want to go back and show you some more examples of those heat problems that you're learning how to work. In this example, we've got a metal, and it increases the temperature from 25 to 40 degrees Celsius when the metal absorbs some heat. And we want to figure out what is the specific heat of this metal. Now we can compare our answers to the reference tables and come up with the identity of the metal. So I'm going to use that same equation, Q equals Cm delta T. I can substitute in here. The 141.2 joules is the Q value for heat. Remember, I'm looking for the specific heat C. The mass of the metal is 18 grams, and I know the change in temperature is final minus initial, or 40 minus 25 degrees Celsius. Now your units are going to cancel out some here and they'll rearrange. We want to solve for C. So I'm going to do some rearranging to get this. Divide both sides by 18 grams and 40 minus 25 degrees Celsius. When you do this math, you're going to come up with a value for C, 0.523 joules per gram degrees Celsius. Now if you look in your reference tables, you'll find that there is a value very similar to this, and that identifies this metal as titanium. So we can use data collected in a calorimetry experiment to identify an unknown. Here's another example. In this problem, we know the mass of this unknown metal. It's heated to 100 degrees Celsius, and then it's put in a calorimeter with the water. And the water warms up from 22 to 27 degrees Celsius. We're trying to figure out the identity of the metal. So if you think about using Q equals Cm delta T, there's really not enough information about the metal to do that with. But what we can do is work a problem with the water first and use some of that information to help us later. Let me show you. For the water, if we plug in to Q equals Cm delta T to solve for the heat that the water absorbed, we're going to get Q equals 4.18 joules per gram degrees Celsius. That's the specific heat of water from the reference tables. I know I have 40 milliliters of water. Remember, for water, a milliliter is the same thing as a gram. So I plug that in, and I know the water warms up to 27 degrees. So I plugged in 27 minus 22 degrees Celsius. When we solve for Q, I find out that the water has gained 836 joules of heat. Now, remember the law of conservation of energy. All the energy gained by the water had to be lost by the metal. So 836 joules was given off by the metal. That was an exothermic process. So I'm now going to be able to plug into that same equation and solve for the specific heat of the metal. That will give me its identity. I plug in negative 836 joules because the metal is giving off that heat. It's exothermic. The specific heat is what I'm looking for. The mass of the metal is 11.18 grams, and I plugged in the change in temperature. I know the metal ended up at 27 degrees, just like the water, and it started at 100 degrees. When you rearrange to solve for C, your problem looks like this. Those negatives are going to cancel one another out, and I come up with a specific heat of 1.024 joules per gram degrees Celsius. Once again, go to your reference tables and see which one is similar, and I think you'll find we're very close to the value for magnesium. So that's just an example of how you can use a calorimeter to collect data and solve for an unknown. Talk to you next time.